Okay, we are going to be beginning a new unit today. As a matter of fact, Unit 9 and Unit 10 both are going to deal with three-dimensional shapes. We've pretty much pounded the crud out of the two-dimensional shapes as much as we can. Now we're going to look at the three-dimensional shapes, which are typically referred to as solids. Okay. Um, Also keep in mind, if you managed to miss class yesterday for whatever reason, we did do the required writing sample number 2. We will not have time to make that up in class, so you'll need to come in about half an hour, either before school or after school, to get that taken care of. Okay, it is a requirement. And also, please keep in mind, I can't remember if I mentioned it or not, but on Monday, of course, they're kicking us out of the upstairs of the high school from 1st through 6th periods. Okay, so class Monday is going to be in room 190. The 190s are those temporary portable buildings that are out over there just on the corner of the campus by where Dotsey and 14th Street come in. So just outside of where the English classrooms are, there's some temp buildings set up out there. That's where we'll be 6th period on Monday. Okay, so you may want to scout that out so you can make sure you get there. I will expect you to be there on time. If you don't get there on time, get you a tardy just like any other day. Okay. All right. We do have some notes to take on solids. Okay. Just like when we get into anything new, we're probably going to have a whole bunch of new vocabulary. Okay. A little bit of background here. Scribble something down if you see something you like. Otherwise, just pay attention, follow along. Okay. The term solids. Whenever you hear the word solid, all that's being communicated with you there is that you have a three-dimensional shape of some kind. Okay, no particular properties that go with it or no particular numbers of sides or anything like that. All it is when we say solid, we're referring to a three-dimensional figure. Solids can have a wide variety of properties, therefore it can be difficult to make any statements or properties that apply to all solids. So we'll have to break it down into more specific chunks, and then we'll look at the properties in those chunks. Okay, however, just like with many other things in geometry, solids come equipped with their own vocabulary to describe their various parts. So we're going to get a bunch of new vocab. Okay, and like many other things, if we don't get a good grasp of the vocabulary, the entire chapter can become very difficult to have success in. Because let's face it, some of you struggled all year long because we never bothered to get the vocabulary at the beginning of the year. So the class has kind of been speaking a language that you haven't really understood. Okay, so don't let the vocabulary get a hold of you. Okay. And let's take a look at some of this stuff. Okay, some of these terms you're going to be familiar with. Some of them you're not going to be familiar with. Some of them are going to be old terms that we're going to find yet another new definition for. Okay, all three-dimensional solids are built out of two-dimensional polygons, which are called the faces of the solid. Okay, this is why we wait for the three-dimensional stuff until after all of the two-dimensional stuff is done, because that two-dimensional stuff ends up building our three-dimensional solids. Okay, so all the properties and all the little formulas and anything that we've come across all year long dealing with rectangles, squares, triangles, trapezoids, regular polygons, circles, all of that stuff is still going to apply because it's going to show up in our three-dimensional solids. Okay, and when it shows up, those will be called the faces. Okay. However, most of the time, this definition that I just gave you of what we call the faces, they are typically not just called faces. Typically, they are separated into two different categories. We're going to look at those two categories here in just a moment. Okay. The only time you typically hear the term just generically on faces is if a question simply refers to how many faces a solid may have. Okay. Now back to the two different categories of faces. The first that we're going to look at are what we call the bases of the solid. Now we're going to get a better definition of bases here in a little while, but for right now, just understand that in a solid, you may have one base, you may have two bases, or you may not have any bases at all. The determination of whether you're going to have one base or two bases or no bases at all will depend on what kind of a shape it is, and I'll tell you what to look for here in a few moments. Okay, so there may be one, two, or no bases at all in a solid. It simply depends on the solid. The second subgroup of our faces are what are referred to as the lateral faces. Okay. Now, the lateral faces, just generally or simply speaking, lateral faces are the sides that are simply not the bases. It's going to be very important to us to identify which sides are the bases. It's going to bring us a lot of information knowing which sides the bases are, and in fact, the formulas that we're going to end up working with on surface area and volume, they are going to refer specifically to the bases. So if we don't get the bases identified correctly, that's going to cause us to plug bad information into the formulas, which of course will bring us a bad answer. Okay. But if you figure out the language between those two, you have the bases, and everything that is not a base is called a lateral face. Then you could probably figure out on your own this next statement. If you were to add up all of the total number of bases and lateral faces together, then that is the total number of faces. And in plain English, what that means is there's nothing else. Nothing else builds our solid except for bases and lateral faces. Okay, now, everywhere that these faces join together, a line segment is formed. Okay, now like we said, all of our sides are nothing but two-dimensional shapes. So we've got polygons. Those polygons are going to hit each other, and where they hit each other, it's a line segment. And those line segments are called edges. Okay, you may have heard this vocabulary before. It's not a difficult term to understand. Okay, but anywhere two polygons join together, a line segment is going to do the joining, and those line segments are called edges. Okay, the number of edges in a particular solid will vary directly upon what kind of shapes the solid is built out of. It is possible that a shape can have 12 edges like this one does. It could have more edges than that. It could have even as few as 2 edges or even 1 edge, or even some shapes that we'll see that don't have any edges at all. Okay, so it just depends upon the particular shape and how it's constructed. But those are your edges. Okay. Now these line segments, these edges, they're going to bump into each other as well. And everywhere that edges join together, a point is formed. And that point is called a vertex. Now, if you remember somewhere back in the neighborhood of 5 to 6 months ago, I told you you'd probably eventually learn to hate the word vertex because we would redefine it several times before the year was out. I believe this is the 4th definition that we have for the word vertex. Okay, and this one applies to solids. Anywhere that your edges bump into each other, that's a vertex. And just like with the edges, the number of vertices will depend upon what the shape has got, what the shape is built out of. It is possible that you'll have many, many vertices in a shape. It is possible that you can have all the way down to just a handful of vertices, maybe even 2. There are some shapes that only have 1, and there are some shapes that don't have any vertices at all. It'll simply depend upon the shape, but those are the vertices. Okay. Now, here is something that is new. Okay, if you've been through geometry before, you definitely need to pay attention to this because this is a demand they have never put onto geometry students before. There's a mathematical connection between the number of faces, the number of edges, and the number of vertices. And this formula is not a new formula, but it's the first time I've ever heard of them expecting geometry students, high school geometry students, to know it. Okay, so we do have a new formula we're going to have to become familiar with. And this formula is named after the gentleman that came up with it, and it's called Euler's formula. And that is the way his name is pronounced, even though that's not the way it looks. Okay, but Euler somehow was able to discover that in a solid, the number of vertices, if you subtracted away the number of edges and added in the number of faces, that the result of that little calculation would always result to 2. How he came up with that, I have no idea. Okay, but it does work. I wish I had some cutesy little way for you to remember it, but I don't. Matter of fact, maybe I need to offer some extra credit if somebody can come up with a little acronym or saying or something like that that can help us figure this thing out, or a way to remember it, because we are expected to know it, and it's not going to show up on the formula chart. Okay, but vertices minus edges plus faces is always going to equal 2. Okay, it's not a difficult calculation, and it's not difficult to understand the problems. Okay, we just have to be able to remember the formula and then put it to use when we see the problem. Okay, these problems look something like this when we run into them. There's really only one screwball thing that they can really even do to us on these questions, and I went ahead and did it to you on this question just so you can see it's not a difficult thing. Okay, if a solid were to have 2 bases, 3 lateral faces, and 6 vertices, how many edges does it have? Okay. Well, anytime one of these problems starts pulling out information about vertices or faces or edges, and then starts asking you about vertices or edges or faces, that's where you're going to need to think, oh yeah, that's that Euler's formula, vertices minus edges plus faces equals 2. So hopefully we will get that thing memorized. Hopefully somebody will come up with some way we can remember it. And then all you have to do is plug in the information that you know and solve it. Okay, it's no different than any other equation. We just have 3 variables. We got to plug 2 of them in, just like Pythagorean theorem. Okay, so number of vertices. We know the number of vertices this time? Yeah, we got 6 of them, so we'll plug in a 6 there. How about the number of edges? Do we know this one? Uh, Edges is the variable, right? That's what we're looking for. And the number of faces? 3, and that's where they're going to get you right there. It's not 3. It's 5. Remember, the word faces is all of the bases and the lateral faces pulled together. So F is going to be a 5. And that's about all they can really do to you on these questions. So just pay attention, to what you're writing down, and then solve for your variable. In this case, our variable is a negative e sitting right in there. We got 6 plus 5, which is 11. We could subtract that to the other side. 2 minus 11 is negative 9. We have a negative e. We don't want a negative e. We want a positive one. So we would divide everything by negative 1, which would flip all the signs, and that would make this particular figure have 9 edges. Okay. And just in case you might be curious, what kind of a figure could have 5 faces and 6 vertices and 9 edges? Okay, well, it could be this guy. Okay, there's other possible examples. I just threw one together just for grins. Okay, but Euler's formula is very simple to work with, but we do have to get it memorized. We got to have it in our brain just in case it's needed. Okay. All right, back to the vocabulary. Okay, I already said we learned to hate the word vertex because we have like 4 different definitions for it now. Oh, now we're going to have 5 definitions for it. Some of our solids are going to be pointed on one end. This location is called the vertex of the solid. Now, if that language sounds familiar, us calling something the vertex of a figure, you may recall that back in probably October or something like that, we spent some time talking about isosceles triangles. And isosceles triangles had a location that we called the vertex. Okay. Now, what we're looking for, okay, is like I said, some figures are pointed on one end, and that's that's not a very highly technical definition, okay, saying that a figure is pointed, and if it's pointed, we're going to call it the vertex, because depending on how the shape's built, it may not look very pointed at all, okay? But the key here is like we said, some of our figures are only going to end up having one base. If they only have one base, then across from that base, we will have this quote-unquote pointed location that we will call the vertex of the solid. Okay, and again, you have to be very careful with the language in geometry, because when we tend to think of words like base, the word base usually makes us try to think about something on the bottom. Well, solids are no different than anything else that we've seen this year. Okay, the base can be anywhere. Okay, in fact, if I had to place a guess, I would say that when it comes down to solids, it's a good strong chance that they may not set a figure on its base. They may turn it over on its side or turn it upside down just to make sure that you know what you're talking about when you start plugging numbers in to formulas. Okay, but again, as you can see, these two particular figures, and we'll worry about the names of these figures tomorrow, which I think everybody probably already is familiar with these guys. Okay, but when you have a figure that only has one base, wherever that base is located at, across from that, your figure will come to a point, and that point will be called the vertex. And I'll give you the same cautionary note that I gave you before when we were talking about isosceles triangles. Be very careful. Okay, all of the places where the edges join together are called vertices. That's what we saw when we talked about the isosceles triangle. It had 3 vertices, but there was only one of them that we called the vertex. The same thing's going to be true with our solids. All of the corner points are vertices. There's only one of them that is the vertex, if it even has that one. Okay, so be careful. All the places where edges join together are still vertices, but there's only one place called the vertex. So if you think about this figure over here on the right, it's very possible that a question might ask you about how many vertices it has. Okay, don't get yourself confused. There are 1, 2, 3, 4, 5 vertices in that guy. Okay, but if a question referred to the location of the vertex, that's a different issue. That's where we'd pick on this guy down here at the bottom. Okay, so just be careful, pay close attention to the language, and you shouldn't have much of a problem. Okay, now other times, okay, the figure may not have this location. It may not have this pointed location that we were talking about that we can call the vertex. Now typically when it doesn't have that, then what we do have is we have a figure that doesn't just have one base, we have a figure that usually has 2 bases. Okay, and here's kind of where we're coming back to this. We said we'd kind of define better what bases are. Here's the better definition. Okay, the shapes that when they have 2 bases, what we're looking for is we're going to have 2 opposite congruent faces that are parallel to each other. Okay, so opposite meaning they're across the figure from each other, wherever they are. Congruent meaning, of course, that they're exactly the same size, same shape, and parallel to each other, obviously meaning that they're not going to run into each other in any way. Okay, when that happens, then we have a figure that is going to have 2 bases rather than just one. And if it does have 2 bases, then it will not have the vertex. Okay, so looking at these particular 2 figures here, okay, these fit the definition. We can find a location inside of these figures that have 2 opposite congruent faces running parallel to each other. Like on this rectangular prism over here, okay, the rectangle on the top and the bottom, they are opposite, they are congruent, they are parallel. We can call those bases. And actually, you could call the left side and the right side instead of top and bottom. We could have called the left and right the base, right? Because they are congruent, they're opposite, they're parallel. We could have done the same with the front and the back, okay? But over here on this guy, okay, you can see we've got circles on each side of it, okay? They're opposite, they are congruent, they are parallel. So we could call those the bases. And again, of course, the bases can be anywhere. It doesn't necessarily mean top and bottom. Okay, now at the beginning we also suggested it was possible that we could have some solids that would not have any base at all. There's only one particular solid that we're going to work with that does this. It's not the only solid that exists, but it is the only solid that a class like geometry is worried about. And of course, you know, shapes that have completely curved surfaces. Okay, particularly the sphere. We'll spend a little bit of time worrying about the sphere, not too much though. Not nearly as much time worrying about the sphere as we did circles. Okay. But anyway, just to bring it to your attention, it is possible that a figure may not have any bases. And looking at this figure, you can probably say, hey, this figure doesn't have any edges and it doesn't have any vertices either because it's just one continual lateral face wrapping around, right? Because if it doesn't have a base, and we said everything that builds the figure has either got to be a base or a lateral face, if there's no base, then the skin of that thing must be just one continuous lateral face. It just continues to go around. It doesn't ever begin, it doesn't ever end, so it doesn't ever really technically run into itself, so there's no edges. And if there's no edges, there can't be any vertices because there's no edges to run into each other. But anyway, we're going to have formulas to follow when solving for various information. You're going to find that the um, majority of the solid type questions that come your way on STAR, some of it's going to be dimensionality, considering what different measurements may exist, what different measurements may do as they change from dimension to dimension. We'll have some nets and things like that, which is something we'll talk about this unit as well. But mostly you're going to be calculating surface areas and calculating volumes, and that is going to largely change as we change from one figure to another figure. Okay, but anyway, those formulas that we're going to be working with on surface area and volume, they are going to refer to a couple of pieces of information very frequently. Okay, so let's take a look at a couple of these. One of them I think you'll be very familiar with, one of them maybe not so much. Okay, but let's have a look. Okay, height. Here's a word that we are very familiar with at this point. Okay, we've been working with height for the last couple of units. And when it comes down to solids, our height is going to be found in one of two places, depending on what kind of solid you have. Now, if we are dealing with a figure that only has one base, then the height will exist inside of the figure, going from the base over to the vertex. And just like with our two-dimensional discussions, your base, whatever you're calling your base, is always going to be perpendicular to your height. I know we're not artists, but if you need a diagram, just do the best you can to scribble it down, or just writing down this definition. It's pretty straightforward. And the other situation is that we may have two bases on our solid. And again, we'll worry about how to name that stuff tomorrow. Okay, but our height will simply be the distance directly in between the two bases. And once again, that means that our height and our base will always be perpendicular to each other, just like it has been for the last few weeks. Base and height are always perpendicular. And lastly, here's a term that I hope you have at least heard. And if you haven't heard it, maybe you've spotted it on the formula chart, because a lot of the surface area calculations do call on this particular term. So a new term to most of us is going to be what we call slant height. And maybe you may have remember it being mentioned a couple of weeks ago on the success spirals. Miss Wyant was doing some calculations on surface area and volume. And slant height is one of the calculations that's needed. Now, it's kind of a strange thing, okay? In geometry textbooks, pretty much everywhere you go, you're going to hear this term called slant height. But for whatever reason, the powers that be, the STAR and the tax people, like to call this one lateral height, which is fine. Okay, but it's a little bit of a vocabulary difference. It's probably to your benefit to know both terms, slant height and lateral height, just in case either one of them happens to show up. The slant height can be found by connecting the vertex of a solid to its base by moving down a lateral face. Okay, well, by that definition, that means that we are not going to have a slant height in any type of a figure except for one that's got one base, because it's only the ones that have one base that have the vertex. Okay, but the slant height goes from connecting the vertex of a solid to its base by moving down one of the lateral faces. So kind of another way of thinking of it is height from the previous slide measures from the vertex to the base by going through the figure, going straight through the figure down to the base. Lateral height or slant height still goes from the vertex to the base, but it won't get inside of the figure to do it. Okay, it'll just slide down one of the lateral faces and measure that distance. It's important to know both of them because those are two values that are called on very regularly. The volume formulas use height a bunch. The slant or lateral height is used on surface area a bunch. So you'll see both the regular height and the slant height used in volume and surface area formulas. Okay, so if you would look at the worksheet, I got some work there on vertices, edges, faces, all that kind of stuff. A few questions on Euler's formula, and that's all.